All right, let's take a look at section 12.4, which is all about the cross product. So, a few learning objectives this time: defining and computing the cross product, and going hand in hand with that, we're also going to look at computing the determinants of 3x3 matrices. So as it turns out, those are going to be pretty closely related. We'll also look at the cross product geometrically, and then compare the cross product to the dot product from the last section. So starting with the definition of the cross product, if we have A as a vector and B as a vector, then the cross product of A and B is the vector, everything that you see before you. It is still a vector in the same space as the starting vectors. So we have A and B are three-dimensional vectors. Their cross product is another three-dimensional vector. And it's this long and somewhat complicated looking equation to come up with all of that. We're going to look at an easier way to remember and calculate that thing. But for now, at least here's the definition. The one thing that I do want to point out is that the numbered components of each of the parts of this cross product. So if we look at the part of the cross product that's in the first position, we should notice that it depends only on letters 2 and 3 in position 1. Then if we instead went to go look at position 2, we'd see that that depends only on numbers 3 and 1, and notably not 2. And if we also take a look at position 3, it depends only on components in positions 1 and 2. Again, notably not 3. So each of the positions or each of the components of the cross product will not contain any components from its original vectors that are in those same positions. But let's look at a couple other properties of the cross product before we move on to actually calculating it. The cross product is a vector, and that vector is going to be orthogonal to both of its component vectors. So A cross B is orthogonal to both A and B, assuming that the cross product is not 0. Then if theta is the angle between those two vectors, then the cross magnitude of the cross product is equal to the magnitude of the individual vectors times sine of theta. Compare that to the dot product, which had cosine theta instead. And lastly, we're going to say this time that our two vectors A and B are parallel if and only if the cross product is equal to 0. And keep in mind that that's the cross product being equal to the vector value 0 rather than the scalar value 0, meaning that that 0 is really the vector 0, 0, 0. I mean, we should just write that in. Equals the vector 0, 0, 0. That's assuming that we're in 3 space, because we could potentially have vectors that exist in more or less dimensions. But yeah, it's equal to the vector 0 rather than the scalar 0. So let's move on and discuss determinants of matrices. So probably at least the determinant of order 2 looks kind of familiar to you. If we have determinant of A, B, C, D, then it is equal to AD minus BC. And we get that by taking AD and subtracting BC. It almost kind of looks like a cross if you do it that way, which maybe that's where the cross product gets its name. Although at the moment we're still just looking at determinants. So we'll put that together in a minute. So that's the determinant of order 2. And then there's an example below where we actually plug some numbers in and calculate it. And then what we're going to really want to do is look at a determinant of order 3. So if we have a 3x3 matrix and taking its determinant, it comes out to the equation listed to the right, where we have each of the pieces of the top row being multiplied into another smaller determinant just of order 2. So if we're looking at calculating the determinant of a 3x3 matrix, it's basically the same as calculating the order or the determinant of 3 2x2 matrices. And if we start to look at where those pieces come from, let's look just at the first piece for a moment, where we've got the first part in the top row, A1, being multiplied by the determinant of all of the pieces that are not in its row or column. So you should hopefully see there that we have the determinant of the matrix B2, B3, C2, C3, if we just read left to right. And so when we're going to look at the determinant in each of these three pieces, we're going to be looking at just the pieces that are not in its row or column. If we do the same thing, but for the middle term, we're going to take A2, and then that multiplies into everything that's not in its row or column, which ends up being B1, B3, and C1, C3. Also notice the negative that shows up out in front of A2. We're going to deal with that in a minute. But for now, just enough to know that all those pieces are coming from all the components that are not in the second column or in the first row. And then we can do the same thing. If we look at the third component, this is now A3, and the determinant we'll look at will be all of the pieces in columns 1 and 2. So if we actually go to multiply this thing out, again, we'll look at sort of doing the cross of that determinant. We end up with A1 times, this is B2C3 minus B3C2. I can already tell I'm going to need some more space for this, so let's just move it all the way over to the left. And then we have the minus A2 times, we'll look at that same cross product, but because this one's negative, I'm just going to draw the cross in different colors. We'll go this way first, and that way. And highlighting it with those same colors, I've got, that was B1C3 minus B3C1. And then into the final piece, A3 times a bunch of other stuff. I'm just going to move that diagram out of the way because I'm going to talk about it in a minute. We'll go first that diagonal and then this diagonal. We've got B1C2 minus. This next piece is B2C1. And if we check this back up against our definition of the cross product, we should see that it looks pretty familiar as it stands. But one thing I want to do is notice this negative that's hanging out right there. So when we're going through the cross product, there are a couple of different conventions for how to write it out. This is the one that the textbook uses, where the middle term in this determinant is negative. I prefer a slightly different one that I'll show in a moment because I think it's easier to remember. And it's going to tie into that diagram about positive and negative in the upper right. But first, let's just take what we currently have, but rearrange the terms so that we can kind of factor out that negative. So if we just copy and paste, we already have, but for some reason it got moved all the way over there. And I'm going to change that negative to a positive. But doing so means that I'm going to have to multiply the negative through all the terms on the inside, meaning that that magenta term would become negative while the green term becomes positive. So they would just have their orders reversed. And now that I've written it out this way, I can still have all of the green terms coming first with all of the magenta terms coming second. Because that middle term had the negative in it, sort of why I did the colors backwards in the middle piece. because ultimately, after multiplying it out and now changing it so that each piece is positive instead of the one awkward negative term in the middle, I can come up with a bit of a pattern that emerges. So now let's finally talk about that little diagram that I have drawn up in the top, where it's got the sequence 1, 2, 3, 1, 2, 3. So it's just 1, 2, 3 listed out twice and ordered in terms of its first, second, and third position. First position being purple, second being yellow, third, and then third being magenta. So a handy way for remembering how these terms all come together. As I said from earlier, in the first position, I'm only going to have components in the 2 and the 3 position. And all of the positive terms are the ones that move from left to right in the sequence. So for example, I've got B2C3, which is going forward in the sequence from 2 to 3. Right, that's moving left to right in the sequence, so that term comes out positive. Compared to B3C2, which moves backwards in the sequence. I go 3, then 2, which following my sequence, that means it's negative. And looking at the first and the third terms, it's pretty easy to kind of put those together, because I can see over in the third term, I have B1C2, so moving from 1 to 2 is forwards, that's the positive piece. And then the negative piece is B2C1. So that one would be going backward in the sequence. The only one that's tricky is the one in the middle. Since, if you were just thinking about numbers getting bigger, going from 1 to 3 would seem like it's positive, and then 3 to 1 would be negative, but that's actually not quite the case. Because if we're following along in our sequence, going from 3 to 1 would be positive. Because I don't want to skip any numbers when I'm going through the sequence. So after 3 comes 1, meaning it's 3, 1 that's positive, rather than 1, 3 that's positive. So yeah, then the 1, 3 part would be negative. So I prefer to remember it this way, and we'll look at another trick for kind of helping us remember that in a moment, as we actually look at the cross product. But it's entirely up to you which way you kind of want to remember it, because it is just about doing a lot of computation when it comes to these types of problems. So I'm going to grab my same little position guy and drag it down here, because I may want to use it in this next example. So let's compute the cross product. So the cross product is going to be the determinant of the matrix that I've written down before us. I've also written it down 3 times so that I can kind of break down each part of the cross product. And so the 3P, if I'm taking A cross B, I will set up the determinant in this way, where I have the standard basis vectors across the top, or the top row, and I'm going to use those to come up with each component of the cross product. So in this first piece, I'm going to want to compute the I component of my cross product. And if I just block off the top row and the first column, because I'm looking at the I column, then I just want to take these 4 pieces in the determinant, because since I'm going positive, I want to read left to right. If we go into the middle piece, I'm just going to color this in a different color because this is the one that kind of works out a bit differently. I'll again block off the row that I'm in. But unlike the first determinant that I tried to block off, J is in the middle, which means if I just block off J, I kind of need 2 lines to block it off, and I don't have one complete section, which is why this one is kind of weird. Sometimes it's written out with a negative, but I'm going to hopefully show a better way, or at least a way that I like a little bit more. Since I'm in the second position, I want to read from left to right, which means I would read into 3 first. So I would start with the A3, B3, and then wrap around and come back to get A1, B1. So that this middle matrix should look like, if we just put this in, I've got A3, B3, and then A1, B1, as opposed to rewriting it with 1 in the first column and 3 in the second column. Because again, I want to follow that pattern, the one that's hanging out over here, and I want to follow it in the positive direction. So after 2 comes 3 and then 1. So this is that determinant times the vector j, basis vector j. And then over here, should probably write down the first one as well. A2, B2, A3, B3 times my vector I, basis vector I. And then add to that the next piece in this component, which will be the k part. And then I'll come back to blocking off the third column in the top row, meaning that the determinant that I get is that one in green, since again, I'm going to read from left to right, which really means I'm going to wrap around. I'll start by going to the right, which means wrapping around back to the beginning of the matrix. So this one, I've got A1 and B1 in the first column, and A2, B2 in the second column, and my vector k. Once again, I'll point out that in the I basis vector, so in the first component, I don't have any terms that depend on number 1. So none of the first components are in the I part of the cross product. Just like in the second part of the cross product, I don't have any number 2. I have only 1 and 3 showing up. And in the third part, I have only numbers 1 and 2 showing up in the cross product. So if we then go through and do that cross product thing again, this thing should be A2B3 minus A3B2 times I. Let's actually scooch that a little bit over to the left. Plus, this will be A3B1 minus A1B3 times the vector j plus A1B2 minus A2B1 times the basis vector k. And this is the cross product of A and B. So the vector A cross the vector B. So rather than trying to remember one long formula for the cross product, I think it's way easier to remember that the cross product is just a series of determinants, or rather the determinant of one 3x3 matrix, which then gets broken down into 3 2x2 matrices. But enough theory. Let's actually apply this thing. So evaluate the cross product of 1, 2, 3 and -2, 1, 0. So I've already gone ahead and written out what that determinant should be. So let's break that down into its smaller determinants. So this should be the matrix 2, 1 in the first column, 3, 0 in the second column, times I plus, and here's where I'm using the positive notation for the second. So I'm going to need to make sure I put the third column in the third column of the 3x3 and the first column of this 2x2 matrix, and then the first column into the second position of this matrix. And that's multiplied by the basis vector k plus one more 2x2 matrix. That'll go 1, -2, 2, 1. And actually, it's this one that's multiplied by k. I had the color right for the middle one, but that's actually the basis vector j. There we go. Looks a little better. All right, and then we'll actually get a value for each of this stuff. So if I take these cross products, I'm going to get 0 minus 3, since 2 times 0 minus 3 times 1 for the I position, plus I'm going to get 3 times negative 2, which is negative 6, minus 0 times 1, which is 0, j, and then plus, this looks like 1 times 1 minus a negative 4 times k. Which if we then simplify this thing, and let's also just put it into that standard vector form, negative 3, negative 6, and negative 1 minus negative 4 ends up becoming positive 5. And I suppose we could also color these in terms of the components that they are. Cool. So that's our first cross product example. Also, those colors aren't necessarily standardized or anything. These are just some of the colors that I like. I forgot the hats on some of these vectors. So I'm going to try and stay relatively consistent using these three colors for the three components, as I need colors for examples. All right, if we look at one more example, finding a vector u that satisfies the two properties that u dotted with the vector 9, 3, 1 is equal to 0, and that u dotted with vector negative 2, 4, 0 is also equal to 0. So let's start off by saying that there is one particularly boring example where I could say that u is equal to the vector 0, 0, 0, because that would satisfy both of those two conditions, but again, kind of a boring result because it's just the 0 vector. And there is another vector we could find anyway that'll also do this same thing. So remember from the last section that if the dot product of two vectors is 0, then those vectors are orthogonal, or one of the vectors is 0. Again, kind of the boring case, we're going to ignore that, which means that u should be orthogonal to both of those two vectors. So that means we're going to take the cross product of the two vectors listed. Also, surprise, surprise, it's the cross product section. We're taking the cross product of two vectors. Who could have seen that coming? Okay, so we'll start by setting up our determinant, and it doesn't really matter which one. Well, it does and it doesn't matter which one we list first. But let's do 9, 3, 1 on top, negative 2, 4, 0 on bottom. So since I just brought it up, if I were to have switched the order of those two vectors and put the bottom one in the middle instead of on the bottom, I would have gotten a vector that pointed in the opposite direction of the one I'm going to get right now. So the only real difference between calculating this cross product versus the other is that the other is going to be different by a negative sign. But enough of that. Let's start calculating this thing. So if we get the I component, that's going to be 0, 3 times 0 minus 4 times 1, plus into that next position, 1 times negative 2 minus 0 times 9, plus that third one, I'll have 9 times 4, which is 36, minus 3 times negative 2, which is negative 6. And that's k. Also, let's put the hat on j before we forget. And then we can just put that thing into a vector. I could leave it as the sum of some component times the basis vectors, or I can put it back in standard position, and it doesn't really matter. Either way, it's fine. So -4 in the x position, -2 in the y position, and 36 plus 6 is 42 in the z position. So that's a vector u, in addition to just the 0 vector. As it turns out, there are an infinite number of vectors that would satisfy the conditions provided, since all I need is for u to be both orthogonal to the two vectors provided, but all possible vectors that will work are going to be in the same direction as the vector u that I just found here. And I can either go in its forward direction or in its negative direction and still come up with a result. And then, like I said, there's also, the 0 vector, but, a somewhat boring example. So we wanted to find the exciting one. And it let us practice the cross product. So hooray for us. All right, so visually, what the heck does this cross product look like? So I said earlier, the cross product of two vectors is going to be another vector. And so based on this figure, we kind of get an idea of what it should look like. So it's going to be orthogonal to both A and B. So if I just line it up at the initial points of both A and B, say these are all at the origin, then vectors A and B would determine a plane, and then the cross product would just be orthogonal to that plane. And I touched on it earlier, but let's actually get to that note in a second. First, we'll talk about the right-hand rule, because that's the part that I really needed to bring up here. So I found a decent looking picture in the textbook where it kind of describes the right-hand rule. So if we take our right hand, place it in the direction of vector A, and curl it in the direction of vector B, and again, it's important it's our right hand because we need to have our fingers follow that angle theta in a specific direction, our thumb is going to point in the direction of the cross product. So in this case, it has the cross product pointing up based on the right hand rule. If we were to instead take B cross A, you just kind of hold up your right hand, so make sure it's not your left hand, must be your right hand, put it in the direction of vector B and then curl toward vector A, you'll end up with your thumb pointing down instead of up. So if we just draw this vector, this should be the vector B cross A. And it points down instead. So a couple of things that we should say about this. It is important that this angle theta we're talking about be between 0 and pi, or between 0 and 180 degrees. Since if our angle were larger than 180 degrees or larger than pi radians, we would have curled the other way to get to the vector. So we're going to keep theta in between 0 and pi. And then that brings me to the note that I was wanting to talk about, which is that A cross B is not equal to B cross A. So order is important when we're taking our cross products. So if it's A cross B, then A is the vector that goes on the top in the determinant, while B is the vector that goes on the bottom in the determinant. And if I just switched those orders, then I would come up with exactly the negative of what I started with, B cross A. Let's say that A cross B is equal to the negative of B cross A. So as we can see from the diagram, it would go down instead of up. All right, and then let's compare the dot product and the cross product. So A dot B versus A cross B. So first and foremost, we get two different types of results. The result of A dot product is a scalar, which don't forget, that means it's just a number, whereas A cross B gives us a vector result. That's one of the biggest differences between them, aside from being like two totally different processes. But their results just aren't even the same type of thing. So scalar, if it's a dot product, vector if it's a cross product. Another thing is that if we reverse the dot product, it all works out. A dot B is the same as B dot A. Totally fine. But as we just saw, the cross product doesn't work that way. So A cross B is not equal to B cross A. But the thing that we have instead is that A cross B is equal to the negative of B cross A. Don't forget our hats because they're vectors. Another fancy thing is that if we take the dot product of A and B, we get the magnitudes of our two vectors times the cosine of theta. Let's put it in green to emphasize that it's cosine when we do the dot product, because if we take the magnitude of our cross product, keeping in mind that the magnitude of the cross product is now going to be a scalar value, but the magnitude of our cross product is equal to the magnitude of the individual vectors times the sine of theta. So the dot product is going to be related to cosine theta, while the cross product will relate to the sine of theta, where theta is the angle that's in between them. And finally, we're going to look at what happens if we get 0. So if we have A dot B equal to 0, this implies that our vectors are orthogonal. Versus if we take the cross product of A and B and get the vector value 0, this implies that our two vectors are parallel. Parallel only has one R, but then it's two L's. And also a third L. Cool. So if the cross product is 0, we have parallel vectors, and if the dot product is 0, we have orthogonal vectors. Or, one of those vectors is 0. But that's sort of the boring case, so just assume that neither of our vectors are 0 when we say that. So a couple of more things. So several properties about cross products. The first of which is one of the more exciting ones, is that if we take the cross product of two vectors, that's the same as the negative of the cross product with their orders reversed. And then there are several other theorems here that may be helpful when you're looking at doing algebra with these cross products. But then let's also take a look at sort of what the magnitude of this cross product means. We defined it earlier, but geometrically, the magnitude of the cross product of two vectors is going to be equal to the area of the parallelogram determined by those two vectors. So if I've got vectors A and B listed out right here, you can see that they sort of create a parallelogram. If I just mirror image A and B moving on the right and the top of that parallelogram. So if I were to look at the area of this thing based on the diagrams that are there, I would have the length of side A is going to be the magnitude of A times the height, which based on that triangle that we've drawn out, we can see that that's the magnitude of B times sine theta. And we saw from our definition earlier that this is just the magnitude of A cross B. But actually, this is where that definition comes from. by sort of constructing this parallelogram, we can see that the cross product is equal to the magnitude of A times the magnitude of B times the sine of theta. So really, that's representing the area of a parallelogram that's between them. Or if we wanted to call it a triangle instead, so let's just draw maybe this line right here. Actually, let's do it magenta so it matches the other two vectors. If we take that triangle instead, we could also use the cross product to compute the area of that triangle. It would just be 1/2 of the length of the cross product. And then let's also take a look at the volume of the parallel pipette determined by the vectors A, B, and C, arranged as below. So we can see with these three vectors, just sort of construct a parallelogram between any two of them to come up with the general shape of this parallel pipette 3D object. And if we tried to look at its volume, it should be the height times the area, where here we know that the height, based on what we have written out, should be the magnitude of A times the cosine of theta. We sort of look at where that's coming from. That's our height times our area, which if the area is going to be set up by B and C, we saw from the above example that that should just be the magnitude of the cross product of B and C, B cross C. And then, based on what we know about the dot product, we can rearrange this thing a little bit, maybe make it look a little bit more familiar. This is the magnitude of A times the magnitude of B cross C, which remember is just a vector, times the cosine of theta. And by definition, this thing is the dot product of A and B cross C. Which we can see is the formula that we had for the volume of this parallel pipette. With the one addition of, we're going to call this thing an absolute value, because that dot product could come out negative. And a volume should always be positive, and so we'll just take the absolute value to make sure that we always have a positive value for the volume.